Okay, let's have the second example on fluid pressure on plane surfaces. So here is the second problem. A vertical trapezoidal gate in the face of a dike is subjected to water pressure on one side. The upper horizontal edge is 1.2 meters below the water surface and is 1.5 meters long. Two edges are vertical and measure 1.8 meters and 2.4 meters each. So determine the total pressure or the force on the gate, one face of the gate. The second, the distance of the center of pressure vertically from the top horizontal edge of the gate. Then number three, the distance of the center of pressure horizontally from the shorter vertical edge of the gate. So I'll just present one way. The other way, you may solve this by integration if you want. So this is the figure and you have to check. We have vertical edges 1.8. This is the entire length here is 2.4. So if we separate the areas into rectangle and triangle, then the triangular part will have vertical, this length is 0.6, 2.4 minus 1.8. So locating the centroid of each area. So this is the centroid of the rectangular part. So the distance vertically from the water surface is 1.2 plus half of 1.8, which is 0.9. So 1.2 plus zero point 0.9 is 2.1. So that's barred H of the rectangle. For the triangle, this distance is 1/3 of zero point 0.6, so 0.2. So vertically from the water surface, 1.2 plus 1.8 is 3 plus 0.2. 0.2 is 1/3 of 0.6, so 3.2. That's barred H of the triangle. So of course, the center of pressure for the rectangle is directly below the centroid of area because the area is symmetric with respect to the vertical axis. So that is denoted E sub r, the distance between CGR and CPR. This is the centroid of the triangle. Again, its distance from the liquid surface, water surface, 1.2 plus 1.8 plus 1/3 of zero point 0.6, so that's 3.2. 1.2 plus 1.8 is 3 plus zero point 0.2 is 3.2. So the location of the center of pressure is not directly below, so it's somewhere here to the right, and we need to solve for the vertical distance between them before we can solve the length of the line through the center of pressure, and the midpoint of that line through the center of pressure is also the center of pressure. So that's why this is barred H of the triangular part 3.2. This is E vertical for the triangle, and the horizontal distance, let's call that E horizontal for the triangle. So this is where F of rectangle FR acts. That's through the center of pressure, and it is acting here, so that its distance from the left is 0.75, half of 1.5. For the triangular part, it's acting here. Let's call that FT. Then for the total force, let's locate it somewhere here, and that distance is X sub P. So that's where the total force acts. Let's call that X sub P. The other requirement is this distance here from the top horizontal edge of the gate, Y sub P. So for FR, it is it is FR plus F sub T, and F is gamma barred H area, the formula. But let's separate the areas into two so that it's easy for us to locate the center of pressure by Varignon's theorem later. So using gamma of water 9.81 kilonewtons per cubic meter, barred H of rectangle is 2.1 and the area is 1.5 times 1.8. So 9.81, 2.1, 1.5 times 1.8. So F of rectangle is 55.623 kilonewtons. For the triangular part, Ft is 9.81 times 3.2, then 0.5 times 1.5 times 0.6. 0.5 is 1/2 base times height. So Ft is equal to 14.126 kilonewtons. That's F sub T. Then for the total force, it is equal to FR 55.623 plus 14.126. F therefore is 69.75 kilonewtons. Then for part B, by Varignon's theorem, before we can apply Varignon's theorem, let's solve for ER. So ER is height of rectangle square divided by 12 times barred h, if you can remember. Height of the rectangle is 1.8, so square divided by 12 times 2.1. So E sub R is equal to 9 over 70 meter. Then E sub triangle is height of triangle square divided by 18 barred h of triangle. And height is 0.6 square, 18 over 3.2 for barred h of triangle. So it is equal to 1 over 160 meter. So by Varignon's, so let's solve for the length of the line through the center of pressure for the triangular part by similar triangle. So L of triangle as to this distance is 0.4 minus E vertical of triangle, because the distance vertically of the centroid of triangle to this vertex here is 0.4, because that is 0.2, 1/3 of 0.6, so this is 2/3 of 0.6, so 0.4. So L as to 0.4 minus E vertical of triangle, which is 1 over 160, equals 1.5 as to 0.6. Solving for L, it is equal to 63 over 64 meter. Therefore, the centroid of the center of pressure of the triangular area is equal to 1.5. Its distance from the shorter vertical leg is 1.5 minus half of 63 over 64, which is 63 over 128 meter in our substitution later. So by Varignon's theorem, let's solve for this y sub p first. We have moment of the force, which is 69.75 times yp about the top edge, equals moment of the force through this center pressure of the rectangle, 55.623. Its distance is 0.9 plus ER. So 0.9 plus ER, ER is 9 over 70. Then plus force of the triangle, 14.126. The distance from the top edge is 1.8 plus 0.2, so that's 2 plus E vertical of triangle. So 14.126, quantity 2 plus 1 over 160. E vertical of triangle. 2 is 1.8 plus 0.2. 0.2 is 1/3 of 0.6. Then we add E vertical of triangle. Solving for yp is 1.227. So it's the answer there. Then by Varignon's theorem again, for x sub p, 69.75 times xp equals 55.623 times half of 1.5. Simply this is half of 1.5 because it is a rectangle. So 0.75. Then plus 14.126 times the moment arm is 1.5 minus L over 2. And L over 2 is 63 over 128. So 14.126 times quantity 1.5 minus 63 over 128. Solving for x sub b is equal to 0.8022 meters. So that's it for this problem. You may solve this by integration if you want. I suggest that if you solve this by integration so that you will only have one strip, it should be vertical. And the challenge would be the setting up the variables, the relationship by geometry. That's it for this problem.